Hi, welcome to another session of Circuits and Networks. In today's class, we are going to learn about three-phase circuits, and this we are going to treat as class 1. So, when we are going to listen or when we want to hear about this three-phase system, what immediately comes into our mind is about these sinusoidal waveforms. You can see you have RYB sinusoidal inputs. They are arranged in zigzag fashion. This type of arrangement of sine inputs are generally treated as three-phase circuits. So we are going to learn in depth about this three-phase system in our future classes. So we'll start with the basics of three-phase circuits. So three-phase system. What do you mean by a three-phase system? A three-phase system utilizes three separate but identical windings displaced by 120 degrees to generate three-phase voltages. So this is going according to the Faraday's law of electromagnetic induction in induction generator, where you are going to get a three-phase voltage from an alternator, and that voltage is stepped up and it is sent through transmission lines to the distribution end. So we are going to see all the applications of three-phase system in our future classes. Let us go with the basics. So we are taking here x-axis with respect to time and y-axis with respect to voltage. Since we are talking about the generated voltage, so if the three voltages are generated and if they are displaced by 120 degrees, this is how they look like. You can see we have started from 0 and we have ended to 540, and three-phase system designated by RYB, it is shown in your graph, where you have VR as the reference voltage whose value is nothing but Vm sin theta. What is small VR? This small VR is the instantaneous value of voltage which is related to the red sine wave which is shown in this particular graph, whose value is nothing but instantaneous value of voltage is nothing but Vm, that is the maximum value of the voltage. Maximum value of voltage, you can take the reference from the t-axis, that is from this 0 position to this maximum value, that is Vm value sine theta because of sine wave. So this is the instantaneous value of Vr. Similarly, Vy is the instantaneous value of the next wave which is shown in this yellow sine wave form, whose value is nothing but Vm sine theta minus 120 degrees. As we have stated the three-phase system, the phase of Vy, it is different from Vr at 120 degrees electrical. So that is why it is treated as Vm sine theta minus 120 degrees. Then when I am going to talk about Vb, that is the sine wave which is shown in blue line. So that is nothing but Vm sine theta minus 240 degrees. So this is how the three-phase voltages are generated from induction generator, or we call as alternator, in general power system applications. Okay, so after framing these equations 1, 2 and 3, let us see how does a three-phase four-wire system look alike. So this particular diagram represents three-phase four-wire system. What is three-phase four-wire system? You can see we have a sending end where we are denoting as RYB. So the one phase with respect to another phase is displayed at 120 degrees. Imagining the impedances of sending end side as ZS and the receiving end as ZL. So sending end, that is source end, so the impedances are ZS. Receiving ends, the impedances are ZL. All are values in RMS, and that too in phase system. So why it is three phase four wire? You can see RYB, it represents three phase, and why it is four wire? You have this wire 1, wire 2, wire 3 and wire 4. So that is why this is four wire system. So from sending end to receiving end, if the current flows, then IR, which is flowing in the first phase, it is given by Im sin theta. As like we have framed the equation 1 of voltage divided by impedance in general form of resistance will give you the value of current. So the instantaneous value of current in terms of maximum current and sinusoidal system, so that is sin theta, this is the starting current or the reference current which is flowing from sending end to receiving end as IR. Then you have Y, we are coming in the clockwise direction, so that is Y. IY is equal to Im sin theta minus 120, so that is flowing in this way. Fine. Once we are done with R and Y, let us go to B. So IB is equal to Im sin theta minus 240. I hope you understood how we have framed these equations with the help of this particular, the shown it is in the diagram. That is the three-phase four-wire system diagram. Fine. Then what happens to the neutral current? Neutral point is this point which is centered from source end to the receiving end. So IN will be equivalent to IR plus IY plus IB. So this is how we estimate the value of neutral current in three-phase four-wire system. Fine. Now we can broadly classify based upon the connections from source side to the receiving end in four ways. That is star to star form. That is, you can see you have a Y connection over here, a Y connection over here, or you can talk about the star star system. This is one of the way which we connect the star to star connection from sending end to the receiving end. Next, star to delta form. You have a star connection, you have delta connection, where the receiving end is connected in delta form. So it becomes star to delta form. Then delta to star means what? The sending end side is connected in delta form and the receiving end is connected in star form. And finally, delta delta connection, where you have sending end and receiving end both in delta forms. So this is how broadly the three-phase system can be classified into different connections. Right. Now let us frame the relationship between voltages in star connected load under balance system, where we are going to find out the relationship between line voltage and phase voltage. So you can see there is a load connection over here. In this load connection, you have three-phase system. This is the fourth wire. I am taking this one as neutral and I have kept it aside. And RYB is the three-phase system. And IR, IY and IB are the currents which are flowing in this RYB network. So the voltage which is formed between R and Y can be treated as VRY. Likewise, the voltage formed between Y and B can be treated as VYB. And the voltage between R and B can be treated as VBR. These values of voltages are called as line voltages. So in generally they are denoted by VL. So VL is the line voltage of this particular system, which can be VRY, VYB and VBR. And what about the three-phase voltages? Three-phase voltages is nothing but VRN. You have R over here, you have N over here. So VRN, or it can be VYN. You have Y over here and you have N over here. So this is the particular voltage which is nothing but VYN. Similarly, VBN, V is over here, N is over here. So the voltage which is formed between these two is nothing but the phase voltages. In general, they are nothing but the RMS values of these voltages. So as we have discussed, one phase voltage with respect to another phase voltage are displaced by 120 degrees electrically. Then if I talk about the VRN, it becomes V phase at an angle 0 degrees. That is assuming that the voltage has started at 0. Then the immediate phase voltage is VYN, which is displayed at minus 120 degrees electrical. So as VBN, which is displayed at minus 240 degrees. So these all are values are nothing but the RMS values of phase voltage. Let me take these values as equation 5, 6 and 7. Also, we know that VL, that is the line voltage RMS value. This equation 8 resembles the line voltage in RMS form. Okay, once we have framed from equation 4 to 8, let us see what is the ultimate relationship we are going to get in terms of line voltage and phase voltage. Okay, so we have this phasor representation. Sorry, we have this diagram representation, whereas VRN is nothing but V phase at an angle 0 degrees, and V and Y, that is the phase voltage between the yellow wire and the neutral wire, whose value is displaced by minus 120 degrees electrical. So if at all I employ the mesh analysis to this loop, means what? I have R, I have Y, I have N. R, Y, N, and what are the voltage we have framed? V R Y, V R N, V N Y. So what is the relation which we are going to get over here? So I'm going to apply KVL over this loop. I'm going to get V R Y is equal to V R N plus V N Y. With respect to R and N, the voltage is VRN. With respect to neutral and Y, the voltage is V and Y. Therefore, VRY, this particular input, is equivalent to VRN plus VNY. Fine. Let us employ VRN and VYN to this particular equation. So I'm going to get VRN minus VYN. I hope you understood how I have rechanged the equation. Let me treat this equation as 9, and I'm going to place the values of VRN and VYN, which is nothing but placed in phasor forms of V phase at angle 0 degrees minus V phase at an angle minus 120 degrees. In fact, I can change the phase value to the rectangular value in this form. So this is the polar form representation. Now this is the rectangular form representation. So V phase plus J 0 degrees, because we don't have any imaginary component, whereas minus B phase at an angle minus 120 degrees can be obtained as minus of minus 0.5 V phase minus J 0.866 V phase. This is the representation of rectangular system of V phase at an angle minus 120 degrees of polar system. You can make use of your calculator, that is scientific calculator, and change the polar coordinates to rectangular coordinates, where you can substitute polar, shift polar of 1 comma minus 120 degrees will give you the relation in rectangular form. Similarly, if at all I want to change rectangular to polar, then polar of, shift polar of minus 0.5 comma minus 0.866, if at all you substitute, you get the polar form as 1 at an angle minus 120 degrees. This you can cross check with the help of your calculator, but the polar form can be changed to rectangular form in this representation. Fine. If I add these two components, I'll get 1.5 as the real component, whereas the imaginary component as J 0.866 V phase. In fact, when I'm going to change this rectangular form to polar form, take out your calculator, and after switching on the calculator, just press shift polar of 1.5 comma 0.866. You'll get the rectangular value as 1.732 at an angle 30 degrees. This is nothing but the phase voltage. In fact, 1.732 represents root 3 value. V phase as it is at an angle 30 degrees. So you can see VRY, which we treat as line voltage, is obtained in terms of phase voltage with a multiple factor of root 3 at an angle 30 degrees. Now similarly you can obtain the value of line voltage of VYB as well as VBR. So after framing these three equations 9, 10, 11, we can come to a conclusion that V line is equal to root 3 times of V phase. Is it not? Yes. So that is the conclusion of line voltage in terms of phase voltage. In order to understand the concept in much more better way, let us draw the phasor diagram. What is a phasor diagram? If you represent the phase voltages with one another with respect to 120 degrees electrical, this is called as representation of phasor of phase voltages which are displayed at 120 degrees. So let me draw this phasors once again. VRN, VYN, VBN all are displayed at 120 degrees. So if at all I am going to take the negative components of these phasors, this is how I am going to get the negative components. So VYN is over here. The mirror image of this will be minus VYN, or it can be positive VNY. And similarly the other two cases. Fine. Now I can take these two phasors and I can draw a vector which is taking in terms of this VYN in negative side, VR in positive side, so that I'm going to get VRY, which is nothing but the line voltage which is obtained in terms of VRN and VYN with negative. So this becomes the line voltage. It is displayed by 30 degrees electrical. So this is how you represent that equation in phasor form. That is VL is equal to root 3 times of V phase at an angle 30 degrees. This is how it is represented. I hope you understood this phasor representation of line voltage in terms of phase voltage. Likewise, I can obtain VYB such that it is 30 degrees 30 degrees lagging with terms of line voltage. So VY1 it is lagging 30 degrees in terms of line voltage. So VL is equal to root 3 times the phase voltage. And similarly, VBR, the line voltage, is obtained in this fashion. Now what is this blue arrow? It indicates the current. What is that current? The current which is displayed at an angle phi means what? Voltage is leading, current is lagging, and that current is nothing but the current IR. Here, line current and phase current are one and the same. If at all you concentrate on IY, it is also lagging with angle phi. And similarly, IB lagging with phi. So here voltage is assumed to be dominating the current. If I want to represent these values on this graph, I can represent like this, such that IR lags BRN. IR can be phase current or line current. It lags phase voltage by an angle phi. I hope you understood this phasor diagram of star connection under balance system. Let us estimate the active total active power, which is given by 3 times of the power in each phase. So we have V phase is equal to VL by root 3, because VL we got as root 3 times of V phase. So V phase is equal to VL by root 3, and I told you IL is equal to I phase in case of star connection. So 3 multiplied with V phase I phase at an angle cos phi, which will give you the value as root 3 VL IL cos phi. Just substitute the value of V phase is as VL by root 3, I phase as IL. You'll get this value, and that value is nothing the active power. So active power in terms of cos phi. Naturally, the reactive power will be in terms of sin phi. And what could be the value of apparent power? The apparent power would be in terms of 3 V phase I phase or root 3 VLIN. So these are the power relations of star network when the load is balanced. With the same analysis, we can get a relationship between line current and phase current in delta network. So you can see the delta network supplied by RYB. Here the three phase currents are nothing but RY, YB and VR. These are the RMS values of the phase currents. This is how the currents are flowing in the system, and they are displaced at 120 degrees electrical in this fashion. And the RMS value of the line current which is flowing in this particular RYB is nothing but IR, IY and IB. And actually the voltages means what? The line voltages between the RYB system are represented by VRY, VYB and VBR respectively. Now we know that IR is equal to I phase at 0 degrees, IBR is equal to I phase at minus 240 degrees from the previous equations. Now if at all I employ KCL at node R, then IR it is incoming. You can see IBR it is also incoming, whereas IRY it is outgoing. So I can write IR plus IBR is equal to IRY, so that IR will be equal to IRY minus IBR. After this equation is framed as 6, just substitute the value of IRY and IBR. So I have substituted the polar values of IRY and IBR in this form. I can change this polar into rectangular by this combination, that is I phase plus J0 minus I phase at an angle minus 240 degrees. That is more, you have to take your calculator, switch off the calculator, press shift and press rectangular of 1 comma minus 240. You will get the value as minus 0.5 and J of 0.866. Let us combine the value. So I'll get the value of IR which is equivalent to root 3 I phase at an angle minus 30 degrees. So this is the relation of currents in delta system, which is also equal to IY and is also equal to IB. So after framing the equations as 7 and 8 under Roman values, I can draw the phasor diagram based upon the equations which we have framed under equation 6 and 7 and 8 of Roman. So this is how the line voltages, line voltages are framed. With the help of these two line voltages, I am going to get the phase voltage as IR, then IY, and finally IB. Assuming that voltage is leading the current, so VRY, VYB and VBR will be in this fashion. So what would be the power relations? Power relations as it is, you have 3 V phase, I phase, cos phi, where V phase is equal to V line for delta network, because in parallel circuits voltage remains the same. So line voltage is equal to phase voltage, whereas phase current is equal to IL by root 3. So if you substitute these values over here, you are going to get the total reactive power whose value is nothing but root 3 VL IL sin phi, or 3 times of V phase I phase sin phi, and the apparent power would be 3 V phase I phase or root 3 VL IL. So in today's class 1 under 3 phase circuits, we have studied about the relationship between voltages and currents for star and delta network. I hope you like this video. Please share among your friends, subscribe to this channel and please press the bell icon for the future notifications. Thank you.